What we're going to do to start chapter 3 is talk about what are called vectors. Okay, vectors. And we're going to define and understand what they are. We're going to talk about calculating vector components. And then we're going to add and subtract them graphically and algebraically using trig. Okay, using the trig knowledge that we learned in the last, 4 or 5 days. So, a vector. A vector is simply a quantity that describes both. I put noth. That should be both. Both, I'll correct those in the notes. Both a magnitude and direction. Magnitude, put in parentheses, means amount. Amount. So for example, velocity is actually a vector. If I say I'm moving 1 meter per second east, ready? Here's what I would do. Imagine east is to the right and west is to the left. 1 meter per second east would be me moving this way. 1 meter per second west would be me moving this way. So east and west are like negative and positive signs also. So vectors are either indicating east or west, or negative or positive, depending on the problem. Okay, east or west, or north or south, or negative or positive. So a vector both has a direction and an actual amount. Vectors are drawn with arrows. A vector diagram shows arrows. The length of the arrow indicates its amount or magnitude. The direction of the arrow clearly indicates its direction. The front of an arrow we call the head, the back of it we call the tail. It really doesn't matter that those terms are known, but knowing how to put them together on a graph is going to be important. I'm going to use those words, but I'm not going to quiz you or test you on the words head or tail in those cases. All right, let's take a look now. So first, let's talk about the idea of adding vectors graphically. Imagine I did this, right? I'm going to stand right here, and I'm going to walk across the room. Let's say it's the first vector. Then I'm going to turn and walk all the way over here. Well, that's like taking one vector, stopping, another vector, stopping. What's one way that I could have gotten here without doing that?
You could walk straight from here. Well, if there weren't desks, you could walk straight to there.
And that's exactly what you're seeing here. See the red line? That red arrow is indicating the direct path. So somebody could have gone across the street, then across another intersection. Instead, they could have just crossed diagonally. Right? The shortest distance between any 2 points is from A to B. That's what you're doing here. So what's distance in this problem? What's displacement? Right?
Yeah, that's displacement, and then that's distance.
Very good. The distance I walked is represented by the two black vectors if you summed their magnitudes. If this distance were, say, 5 meters, and this distance were 4 meters, I'd walk a distance of 9 meters. But my unknown here, since this is a right angle, we'll assume it's a right angle for the sake of this. Okay, my unknown here would be the hypotenuse length, and that would be the displacement, which would give us the square root of 41. Okay, meters, which is, 6 and change. Gabe, you had a question.
So the vectors can only be straight, right?
Correct. Vectors are not curved. Vectors are not curved.
So that would be the fastest way, would be with only one vector. The more vectors you have, the slower you'd be going.
Sure. That's what you can think of. The sum of these vectors is taking a longer path than going directly across.
Can you have multiple vectors on one line, so like have a vector back to back?
Sure. You could walk a certain distance, stop, and then walk in that same direction, have a vector with another vector. That could be replaced with one vector replacing the two together.
This is where Sobotoa comes in, right?
It's going to come in, but not yet.
But also a question, because it's a right triangle, can you not do 5 squared plus 4 squared equals c squared?
That's where that came from. Okay? So the idea here is that if you want to determine what's called the resultant vector, resultant is the red arrow right here. You could get the same result by walking across the room instead of going around one part and around the other. Right? If I could have hypothetically jumped over these desks, I could have gotten the same result, right? But in a quicker way. The resultant here is the distance or the length from A to B, not going along that route. And let me show you more specifically with the next slide what I mean. Take a look at vector addition. Imagine vector A plus vector B, and we want to figure out what the sum of those two vectors are. The sum of those two vectors, this is not a right triangle this time, by the way. This is not, and you don't need a right triangle for this to work, and I'll explain why. The vector A, its length, if we take a look at it, vector A is what? Let's see. 1, 2, 3, 4, 5, 6, 7, 8, 9 units to the right. And it looks like 1, 2, 3, let's say hypothetically 4 units up. That's what vector A is. Vector A means, it's not 9 actually, I missed the first one. It's 8, because the first one's not included there. Okay, so we're starting here. So we've got 1, 2, 3, 4, 5, 6, 7, 8. Oh no, it is 9, I'm wrong. I can't count. I know, right? Gosh. So we have 9 units to the right and 4 units up. That's what vector A has done. So hypothetically speaking, I could have walked 9 units right and walked 4 units up and gotten to the same spot I'm at. Vector B now goes over an additional, let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 units over. Let's use blue for vector B. It goes 10 units over and upward of, oh gosh, let's see. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. And that's why we use axis labels when we draw a real graph, right? So 17 units up. Well, what is the resultant vector as a result here? R. If you look at R is just this 9 plus 10, right? 9 plus 10 is really 19. And if you count how many boxes over R is 19 units to the right. Okay, 19 units over to the right. And then 4 plus 17 over here gives us 21 units up. And if you were to actually calculate the length of resultant R, it would be 19 units to the right, which is from here all the way to here. Okay, where does that 19 come from? The sum of these two. And then it's going to be from the bottom all the way up to here is going to be 21 units up. And where does that come from? It comes from the 4 here plus 17 here. But the concept of solving graphically allows us to just say, okay, if I have vector A, I could draw it first. So draw vector A, then draw vector B to scale, but starting at the end of vector A. And then if you connect the endpoint of B to the beginning of A, you get what's called the resultant vector. Okay, this is literally the same thing I did with walking across the room, but they're not at right angles anymore. Okay, so the sum of vector A and vector B is called the resultant vector R. R is usually used as a term for resultant vector. Look up here. Notice there's little arrows above these letters. Arrows indicate that it's a vector only. That's all it means. Okay, the little arrows on top mean vector. Your book uses bold font for vectors. Okay, bold. They don't have arrows above them because it's really annoying to put arrows above every letter in a textbook. So it's bolded font they use for vectors. Do we get the idea? Can we practice one of these together? You're literally, all you're going to do is put this on the page, put the next one too, and figure out what the resultant is. And I'll give you a graph for the next one too. LT, nice and loud, read it for us.
Person starts to walk and travels 0.4 miles north before stopping at a sandwich. Then the person walks 0.2 miles east and breaks to read a book in the park for a while. After this, the person then travels 0.7 miles south and another 0.6 miles east. Graphically determine the person's final location with respect to a certain point.
So what are we doing here? We're putting how many vectors together? How many? 4. We're putting 4 vectors together. Now, for the sake of physics in high school, we're going to mainly be doing north, south, east, west, so it's easier to draw those vectors. But in a moment, we're going to see how we can use trig and use angles also. You could do graphical analysis with angles. Imagine a person walks at an angle of 20 degrees. And you could use a protractor and do it. And you could actually calculate that stuff with each angle. I'm not going to do that though. What we're going to do is we're going to start with things that are at right angles. Okay, they're at right angles. So let's begin with our starting point, maybe let's say right here. Okay, somewhere in the middle on the left. Because I know I'm going east primarily, and then north a little bit, but then I'm going back south. So I don't know how much of this graph I'm going to need to use. So I start with 0.4 miles north. right? 0.4 miles north. I'll draw that in red. So that's our first vector. Now, how many boxes is 0.4 miles? What should I do? What do you think, Nick?
Just make one box, 0.1.
I agree. Okay, why does that make sense? Because the highest thing you're getting to is 0.7 miles, and you have at least 7 boxes in directions, so this should work. So, 0.4 miles north, go up 4 boxes with an arrow. There's your first vector. That shows that that person traveled 0.4 miles north. We can call this A if we want, doesn't matter. Call this B if we want, just to have locations listed. All right, after that, what happens? What happens next? Leckham?
So 2 boxes to the right.
Good. 0.2 miles east means 2 boxes to the right. Yes.
Are you always going to give us, like, let's say 1 box equals... Like,
That's for you to decide sometimes. So if I give you just a graph, you should utilize the problem's context and say, all right, every box should be like 0.1 miles. Yeah, exactly. That's exactly right. Because of that. If you had, if they had been like 7 miles, 8 miles, 12 miles, 15 miles, then maybe every box is a mile, right? Depending on what the problem gives you. Okay, we'll call that point C. This is where the person stops and reads a book in the park for a little while. After that? After that? What do we have next?
0.7 miles south.
So go 7 boxes down. So back those 4 and then 3 more. Brings us here to point D. And last but not least, Aiden?
6. Right.
Good. Okay? So, take a look at the path this person traveled. Question is, graphically determine the person's final location with respect to the starting point. So we need to know not only how far the length is from A to E, but what is this angle now too? So you see how trigs are coming into play? We're going to solve for an angle in a right triangle. Okay, I'm going to show you the right triangle in a moment, but let's connect A to E now. Connect A to E. Use a different color that you haven't used so far. This is going to be what's called your resultant vector. You should really do it with a straight edge. If you don't have a straight edge, use your ID card or back of your calculator. Perfect. I don't have a straight edge with me. Don't use something metal, because metal will show up and metal will conduct electricity, which will show a line. So use this only. Or something plastic, really. It does use an electrical sensor to sense if there's like a finger there, a hand there. That's why a lot of the tips on these nibs are metal underneath this little metal thing. So take a look at that purple line right there. Label that with a capital R. Okay, you can put an arrow over it to show that it's a vector. It's your resultant vector. Now, how do I find the length of that vector? It's actually pretty easy. How do I find the length of it? It's easy if you do something, actually, I should say. It's not easy, obviously. But if you do one thing, it makes it really easy. Yes. Make a triangle. Very good. Make a triangle. So here's my triangle. From A, go down 3 boxes, make this like your corner of the triangle, and make that your triangle.
What's the R?
It's like when you're trying to find a slope when you're a little kid, and you like count the boxes for the slope.
Wait, what's the R?
Resultant. The final, like the final resultant vector is really, that's all it is. No other way of wording it. So go ahead and make yourself a triangle now at this point. Okay, and I'm gonna draw over at this point with let's see, I should use something else. Can I use a highlighter? Is there a highlighter tool?
You're connecting A and E and not
Use rainbow.
A to E. A was the starting point. E was the ending point. See, A was the starting point, and the problem says graphically determine the person's final location with respect to the starting point. So connect the starting point to the final point. What is this rainbow thing? I don't even know. What is that? Is it really a rainbow color? No, it's no color. I don't know what it means. It's just black. I don't know why it's just black. Anyway, here's the triangle. Take a look. I drew over in black. Okay, I don't care about the path anymore, right? We did the path already, so try to ignore the path at this point. So here's my triangle right here. This height is 3, or 0.3. This height is 1, 2, 3, 4, 5, 6, 7, 8, or this length is 8. So I've got a triangle whose legs are 0.3 on the left and 0.8 on the bottom. How can I figure out the length of that hypotenuse? Anybody? Okay, Pythagorean theorem always. Pythagorean theorem. A squared plus B squared equals C squared. C is the resultant. So 0.3 squared plus 0.8 squared equals R squared. Yeah, you've done this in Mr. Hall in geometry class. That's right. Now notice that the 0.3 was down. So technically this is negative 0.3, but since you're squaring it, it's going to become positive anyway. Okay, the net displacement is down, really. So this is really negative 0.3. But if you look at triangles, because you use a Pythagorean theorem, remember, where was your starting point? Your starting point was at A, and you ended up 3 units below it, didn't you? Take a look. You started here, and you ended up down here, which is 3 units down. So this is technically negative 0.3. And this is to the right 0.8 units, so it's positive 0.8. But it doesn't matter, because when you square a negative, it becomes positive anyway.
So technically this person could have just walked south for 0.3 miles and then walked
Absolutely.
west.
Absolutely. Yes.
So does the negative matter?
Not right now it doesn't, but I'm going to explain when it matters. Yes, it does matter, and I'll explain that. So what we get is the following. That's going to be 0.09, that's going to be 0.64, which is 0.73. Square root of 0.73 is going to get bigger. Remember, when you square root a fraction or a decimal, it gets bigger. What do you get, Ant? 0.85. So that's the magnitude of vector R. That's the magnitude of vector R. The question is, what is the direction? And the direction can only be given if you know an angle. So that's the next part we have to talk about now. So with vectors, you find the magnitude, which is the length of the vector, that's what that is, the magnitude, and we put at, and we're going to put an angle measurement, like at 20 degrees northwest, or 15 degrees southeast. So start at your starting point, everybody. Okay, put your finger here. To get to E, you have to go south and then east. So the direction is definitely going to be southeast. Okay, it's going to be southeast. Now, the tricky part is this. Always put a horizontal line at your starting point. At your starting point, think about a horizontal line here. Okay, visualize a horizontal line. Wherever the resultant vector is, put an angle between the resultant and that horizontal line. It's going to get tricky. Bear with me. Okay, I'm talking about this angle right here. Remember alternate interior angles between two parallel lines? Okay, it's going to come up again. So if you recall, be careful, it's alright. This is the angle we're looking for. This is equal to this one right here.
Oh no!
Okay? So your geometry does Okay. Now, I'm glad a lot of you remember it. I know some are struggling for a second. But again, we want the angle theta between, you should write this in words. You should write this in words. You want, it's just a symbol. You want the angle theta, T-H-E-T-A, theta, between the horizontal line that goes through the starting point, that I kind of just drew in here. See me, I'm covering it over again. Okay, I just drew in this horizontal line. The angle between that and the resultant. That's the angle you're always looking for. Not the angle between the vertical and the resultant. Again, this angle right here. Now, this angle right here can be calculated if you make another triangle, or you can just calculate this angle and recognize that these are alternate interior angles that are formed by two parallel lines and a transverse. Okay? So, again, you could do this. Look over. You could do this. You can make a triangle here. Take a look at the red triangle I'm drawing. You can look at that red triangle and just put 0.3 here, put 0.8 up here, right? Because it's the same thing. These triangles are identical. Put 0.8 up here, put 0.3 here, and calculate that angle. Or you could have just calculated this angle and say that these are the same. Because these are parallel, and this is a transversal perpendicular. Okay? Either way is fine. I don't care. It's up to you to decide which way you'd like to.
Why don't you use the vertical line?
Everything is given with respect to horizontal. It's just tradition. So just to get you used to it. Some books might say things like east of north, which doesn't make sense to say that, but it would be with the vertical. Like here's north, right? If I said 20 degrees east of north, it would mean a 20-degree angle here. If I said, well, let me make believe this is north. If I said 20 degrees west of north, it would mean an angle of 20 degrees here. But almost no physics or real-life applications use the north angle. They use with the horizontal. So you'll hear like 15 degrees southeast. So it really means south of east. So here's east. 15 degrees south of that would be this. 15 degrees northeast means 15 degrees north of east, above east. That's that angle right there. So in our problem, we're looking at southeast, clearly. Because remember, this is our starting line right here. So we start here, we go east, but then we go south of east. So this angle we're going to get in a moment is going to be at some angle southeast. Tonight, here's what you can do. Listen. Figure out what this angle is using your trig work and finish your trig worksheet tonight. We'll pick up with this tomorrow. So trig worksheet needs to be done tonight. Quadratic formula worksheet should have been done already. Most of you did that. Finish the trig worksheet. We started going over the beginning. Finish this problem, get the angle, and fill in that blank right there. Okay?